Hello everyone, I am Sonjoy Dey. I am a graduate student at Kansas State University, currently working in Dr. Gurpreet Singh's lab. Today my presentation is going to be on WS2 nanotube embedded SiOC fiber. This is the general outline of the presentation, where first I'll be talking about the research motivation, the materials used, and then the experimental approach. And then I'll be talking about briefly the different analysis techniques such as microscopic, spectroscopic, electrochemical analysis, and post-cycling analysis techniques. Finally, I'll be delivering some concluding remarks. The motivation behind this investigation stems from the previous works regarding the use of different nanofillers with polymer-derived ceramic matrix, which resulted in important, unprecedented property enhancement. Here, I am presenting two such examples, in the first of which a small amount of multi-walled carbon nanotube was incorporated into PDC fibers, resulting in 500 times higher electrical conductivity than the bulk sample. In another study, other nanofillers such as silicon nitride and aluminum oxide were utilized with PDC matrix where mechanical property enhancement was observed. Now, high strength to aspect ratio makes fibers applicable to various sectors. Further reinforcements with nanomaterials further improve certain properties. Here, I am providing four such examples, in the first of which, a small addition of graphene to polyacrylonitrile-derived fibers resulted in twofold increase in mechanical properties. In a similar study, carbon nanotube fibers were directly spun from aerogel, which showed mechanical properties considerably higher than fibers commercially available nowadays. Hexagonal boron nitride is another nanomaterial which was utilized with polyvinylidene difluoride derived carbon fiber to fabricate a flexible nanogenerator, using which a capacitor of 2.2 microfarad was charged up to 3 volts. In a different study, another nanomaterial that is currently widely studied in energy storage applications, named Mexene, was encapsulated into carbon fibers, which could be used as a supercapacitor electrode with high aerial capacitance. Getting motivated by all of these investigations, I was determined to utilize chemically robust PDC fibers with a nanofiller for beyond lithium-ion storage applications. The decision of the nanomaterial was also influenced by the high pyrolysis temperatures of PDCs. Additionally, the nanomaterial I chose had to provide additional storage sites for sodium ions rather than Mexenes or carbon-based materials, which can only store via adsorption mechanism. The nanomaterial I utilized is called transition metal dichalcogenides, which have a sandwich-like MX2 structure and a typically layered material consisting of a hexagonally packed layer of transition metal atoms sandwiched in between chalcogen atoms. The TMD material I utilized in this study is specifically tungsten disulfide and is naturally found in crystal form, which can be exfoliated to create nanosheets. However, years of investigation have led researchers to create different forms of WS2, such as nanoflakes, nano honeycombs, nanoflowers, nanowires, which have been tediously studied in lithium-ion battery applications. However, the form of WS2 I have utilized in this investigation is the nanotube. Theoretical calculations indicated that WS2 is an exclusive type of semiconductor with an explicit band gap range depending on their diameter. The figure on the left-hand side shows you the SEM micrograph of a forest of WS2 nanotube. The figure on the middle shows you a TM picture of WS2 nanotubes with multi-volt nature. The SAED pattern on the right-hand side shows six-fold hexagonal spot patterns which are faded, and this signifies the 3D curvature of the WS2 nanotube. The WS2 nanotubes utilized in this study were prepared in Dr. Zach's lab. The PDC precursor used in this study is 4-TTCS or 1,3,5,7 tetramethyl 1,3,5,7 tetravinyl cyclotetrasiloxane, which is available in liquid form and is a cyclic polymer. Preparing WS2 nanotubes embedded within SiOC fibers is a multi-step process, first of which is to produce a solution for electrospinning. In this study, WS2 nanotubes were mixed with precursor oligomer to form a black liquid solution for electrospinning. Assuming that everyone here understands the electrospinning, I am moving on to other steps where the ASPEN fiber mat was cross-linked and pyrolyzed at certain temperatures to obtain the final pyrolyzed fiber mat, which is black in color. The proportion of WS2 nanotube mixed with 4-TTCS was an influential parameter for preparing WS2 nanotube containing SiOC fibers. We started out with WS2 nanotube and 4-TTCS mixture of 1:30 weight percent, and the fiber mats were producible up to a proportion of 1:5 weight percent. As the concentration of WS2 nanotubes increased within the solution, we could see a more grayish appearance of the ASPEN fiber mat. Moreover, we could also see a higher weight retention of cross-linking and pyrolysis with increased WS2 nanotube concentration. The pictures on the right show failure during production of ASPEN fiber mat with higher concentration of WS2 nanotubes where films instead of fibers were formed. Microscopic investigation, specifically SEM, revealed the fibrous morphology of the fiber mat at micro to nanoscale. A reduction in fiber diameter as an increase in temperature was observed. Some irregularities were also observed within the fiber mat. EDS color mapping showed the dispersion of all the elements in the fiber mat after pyrolysis. TM images helped us re-verify the fiber diameter obtained from the SEM images. Again, TM images showed us that WS2 nanotubes were indeed embedded within SiOC fibers. Furthermore, from the SAED pattern, the crystallinity of WS2 nanotube was verified along with amorphous rings originating from the SiOC material. From the Raman spectra of a composite fiber mat, the nanostructure or microstructure of SiOC was revealed. Additionally, the Raman spectra at lower wave number showed the presence of WS2 nanotube, and also it was identical to the Raman spectra of the neat WS2 nanotubes. We also wanted to see the evolution of fiber mat during ASPEN to cross-linked to pyrolyzed stages using FTIR spectra. Specifically, the hydrogen bonds gradual disappearing phenomena was observed from ASPEN to cross-linked, and finally vanishing during pyrolysis step was observed. Furthermore, we could also observe the sulfur-sulfur bond vibrations from all of the fiber mats originating due to the presence of WS2 nanotubes. The chemical bond formation of the pyrolyzed composite fibers were analyzed using XPS. A survey scan revealed all the materials present within. We wanted to reconfirm the WS2 nanotubes crystallinity using XRD. A slight shift of peaks of WS2 nanotubes was observed from the composite pyrolyzed fiber mat, which indicated slight oxidation of WS2 nanotubes within SiOC fibers. This phenomena was also confirmed from the high-resolution XPS scan. Finally, different active materials such as neat WS2 nanotubes, SiOC fibers, and composite fibers were tested as sodium-ion half-cell electrodes. WS2 nanotubes react with sodium ions via two different reaction mechanisms, which are intercalation and conversion. These reactions were visible from the peaks of differential capacity curves, which are derived from galvanostatic charge-discharge curves. The same reaction peaks were also observed from the composite electrode, validating the facile encapsulation of WS2 nanotubes within SiOC fibers. The stability of the composite electrode was visible from the gradually increasing rate capability test. This test in real life can be compared with the usage of fast chargers, which degrades the performance of cell phone batteries. From the figure, at even high current rates, the synergistic effect of composite fiber mat led to higher capacity retention along with Coulombic efficiency achievement. To compare the performance of SiOC electrodes in this study with previous literature, here I am highlighting three different investigations, in first of which the capacity obtained from a copolymer of polydimethylsiloxane and polymethylphenylsiloxane derived SiOC ceramic electrodes showed higher capacity achievement than ours. On the contrast, silicon oil derived SiOC showed lower capacity achievement than our study. On the right-hand side, however, a different study tried to investigate the reason behind such capacity achievement of SiOC electrode utilizing density functional theory. Carbon-rich and oxygen-rich SiOC unit cells were modeled in which sodium ions were inserted gradually, and it was found that carbon-rich SiOC takes up more sodium ions than oxygen-rich counterpart. But the volume expansion in case of carbon-rich SiOC is still higher. Moreover, severe silicon-oxygen and silicon-carbon cleavage were observed with large sodium ion insertion at early stages. To investigate the synergistic effect of the composite electrode, we disassembled the half cells and proceeded with further analysis. No apparent color change or physical imperfections of the electrode was observed in such ex situ analysis techniques. The ACM analysis showed the fibrous morphology retention and a 40% increase in fiber diameter, which had a minimal effect due to interfiber void spaces. The XPS analysis of the disassembled electrode showed similar weight percent of WS2 of the neat electrode, indicating the preservation of the WS2 nanotube structure. To conclude, we successfully prepared SiOC fibers in which WS2 nanotubes were encapsulated and utilized the pyrolyzed fiber mat in beyond lithium-ion battery application. Furthermore, our investigation shows that the encapsulation of WS2 nanotubes inside SiOC fibers can help protect the neat TMD material from negative occurrences such as severe volume change and capacity fading during sodium ion insertion. The capacity we achieved is higher than the traditional negative electrode that is used in sodium-ion battery technology. In future, I want to build specific mechanical testing methodologies to inspect the strength of such fiber mat electrodes so that they can be utilized in next generation freestanding, bendable, stretchable electronic devices. Thank you everyone for being here in this presentation. Let me know if you have any questions. Thank you.